In this tutorial, I want to do some calculations involving strong acids and strong bases. The first question I go after is a strong acid, hydrochloric acid. You have to start memorizing strong acids, which are few. Hydrochloric is one of them. When it's reacting with water or it becomes moist, there is 100% dissociation. There is no equilibrium. It goes to completion and it will breaks into fragments of hydrogen ion and chloride ion. Now at initial you have 0.1 mole per decimeter cube of your acid. Concentration of water is not important, it doesn't change much. You have no hydrogen and no chloride. When there is change, we follow stoichiometry. Since the coefficients are 1 for all of them, you will lose minus 0.1 on the reactant side and you will produce the same amount on the product side, 0.1, 0.1. Now instead of equilibrium, I put and because this is just one direction, there is no double arrow. You have none of hydrogen chloride as a covalent compound. You will have 0.1 mole per decimeter cube of hydrogen and you will have 0.1 mole per decimeter cube of chloride. Now chloride is an entity that doesn't have affinity for water. There is no reaction, it's spectator. But hydrogen on the other hand will change your pH. Now anything is negative log of anything, so pH is negative log of H. And we simply calculate it. Negative log of 0.1 mole per decimeter cube is 1. So pH is 1. pH plus pOH is 14. Therefore, we can also say the complementary pOH for this solution is 13. And if you're challenged on concentration of hydroxide, one way is 10 to negative pOH. There are multiple ways to calculate it, so it's 10 to minus 13 mole per decimeter cube. So pH of strong acids is negative log of that concentration. It dissociates 100%. You do not need to show all these equations. I just did it in order for you to reinforce the notion of strong means 100% dissociation. Now let's look at another example, same concentration. This time you have diprotic acid, sulfuric acid. Sulfuric acid is also very strong acid. Diprotic means it has two hydrogens being able to dissociate. Now sulfuric acid, when also touches moisture, 100% dissociates into hydrogen ion plus another species, hydrogen sulfate. Now all of your hydrogen, for sake of simplicity, comes from this first reaction. The second hydrogen from hydrogen sulfate goes through an equilibrium which has very small equilibrium constant, and it gives you small quantity of hydrogen plus sulfate ion. So for sake of simplicity, we are going to ignore this value. Ignore due to equilibrium. And if we do that, which is quite okay, if you take H2SO4, I write the first equation again, and if this is 100% dissociation, giving me H plus HSO4, I'm going to do my direct calculation on this reaction. So initially you have 0.1 mole per decimeter cube. None of hydrogen sulfate. There is a change. Minus 0.1 mole goes, 0.1 mole per decimeter cube comes to life. Same thing with hydrogen sulfate. And if there is an end, there is none of sulfuric acid, you have 0.1 and you have 0.1 mole per decimeter cube. pH is only related to hydrogens. So if you take negative log of that number, negative log of H plus in bracket for concentration is negative log of 0.1, and your pH is 1. Now this is good enough for IB chemistry. Once you are in college, then the second hydrogen you can calculate, and in reality pH is about 0.67, 0.68, but 1 is good enough calculation. Sulfuric acid, strong acid. So for strong acids, just directly calculate pH once you have the concentration. Now let's talk about bases, strong bases in this segment only. For example, sodium hydroxide. You should remember group 1 and group 2 hydroxides are strong bases. So let me change the color to white. So sodium hydroxide is going to dissociate 100% to give you sodium ions and hydroxide ion. Aqueous, aqueous. This could be solid form dumped in moisture and it breaks into fragments. So initially you have 0.1 and you have none of sodium, none of hydroxide. When there is a change, negative 0.1 mole, positive on the product side, plus 0.1. And when there is an end, none of this ionic compound is left. You will have 0.1 mole per decimeter cube of sodium, which has no affinity for water, stays and floats in the solution, and 0.1 mole per decimeter cube of hydroxide, which will change your pH. So, but calculate pOH because that's OH that you have, and then go after pH. Is negative log of OH, so it's negative log of 0.1. So pOH in this case is 1, and pH is 14. Take away that, which is 13. If you're interested in concentration of hydrogen, it's 10 to minus 13. Of course, this has unit mole per decimeter cube. Now let's look at the last one that I want to talk about is another strong base, barium hydroxide. Now this doesn't follow the same assumption as sulfuric acid. This time barium hydroxide, when you do write ionic equations, when it touches moisture, it breaks into one fragment of barium 2+, it's group 2. It also has 2 hydroxide. Either way, you should bring this charge to life. And it will give you 2 hydroxide ions, twice as much. And this is crucial. This is really twice as much. There is no equilibrium involved here. So initially, if you have 0.1 and none of barium, none of hydroxide, there is a change. Minus 0.1, it all goes away. You will produce plus 0.1 and you will produce twice as much of hydroxide. When there is end, you have 0 barium hydroxide, you have 0.1 barium mole per decimeter cube, but barium is not important, it's not reacting, and you have 0.2 moles per dm cube of hydroxide, which is important. Now we can calculate pOH, which is negative log of OH, in this case is 0.2, and the number is 0.69, and pH is 14. Take away that, which is 13.3. So slightly stronger than sodium hydroxide of the same concentration. Be able to write net ionic equations. If you are challenged on hydrogen concentration, it's 10 raised to negative 13.3, but crunch it in your calculator and write with some decent significant figures, of course, mole per decimeter cube.